All right, it's 3 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today?
Pretty
good. Good to hear. All right, so today we're back on to ANSYS, and so we're doing an activity in the second half. From here on out, our ANSYS activities are going to take a little bit of a shift, and so I would say activities 1 through 3 kind of cover. I would consider those to be ANSYS basics. And so, we basically just focus on just the basic ANSYS process of, geometry, mesh, boundary conditions, solution. All right. We didn't do anything too exotic with those, and I think, some of you who are already working on your projects, I think you've already seen that there's more advanced features within ANSYS that you would like to use. Things like different types of boundary conditions or different types of meshing settings. And so that's great. So I'm glad you guys are exploring all that ANSYS has to offer because there's a lot. And even within this class, I would say that we're still only kind of just scratching the surface of what ANSYS can do. ANSYS at the end of the day, it's designed to be a generalist software. And so what that means that, they're trying to cater to almost everything. I wouldn't say that they're the best at everything out there. There are kind of more dedicated softwares that work in very specific applications and very specific scenarios. But, but because of that, they do have a lot of features. And so today with ANSYS Activity 4, we're going to be going over some specialized element types called shell and beam elements. And we're going to talk about kind of under what situations that you want to use those and, what benefits that you get from that. Okay. So what we covered today, I wouldn't say is, you're not going to use shell and beam elements in a lot of your simulations. So, as we go through ANSYS Activities 4, we'll do ANSYS Activity 5 next week and then 6 in the last week. Just kind of keep in mind that, these are not, these more advanced features are not kind of what you're expected to do in every single ANSYS job, but they can be very useful in certain niche scenarios. Okay. Shell and beam aren't that niche. They are used quite a bit, but they definitely don't make their way into every simulation. Okay. Okay, so just like our other activities, we're going to spend the first half of the day just kind of preparing for it. So we have kind of a lecture that goes along with the activity, and then second half starting at 4:30, we'll be doing the activity itself. Okay. All right. So some announcements. Remember, midterm project is due this Sunday. It does seem like a lot of people are starting to work on it, which is good. Gotten a lot of questions in office hours over emails, and so definitely keep them coming. ANSYS Activity 4 is assigned as of today, but it's not going to be due until next Wednesday. So you'll be able to work on it after the midterm project is due. Okay. So for the rest of this week, up until Sundays when it's due, you can just focus on just the midterm project. Okay. All right. Any questions I can answer before we get started for today? Okay. All right. So let's go ahead and get started. Okay. So the subject for today is shell and beam elements. Okay. So shell and beam elements are specialized element types. Okay. So up until this point, we've covered the basic element types, and so the ones that you'll see basically in almost every finite element simulation. Okay. So things like and we're going to assume we're just in 3D at this point. So typical 3D elements. Like the tetrahedron and hexahedron. All right, so those are your kind of two standard options for element shape. And of course, both of those have options for linear and quadratic forms, right? But the tetrahedron and hexahedron, we often call these the solid element types. The reason being is that they are essentially three-dimensional shapes, right? So tetrahedron is our four-sided pyramid, or hexahedron is our block, okay? Hence, they kind of create kind of a solid object themselves, okay? So these are the standard elements to use because they are what we use to fill 3D space. Okay. And for most situations, they work pretty well, right? But there are situations where these types of elements do struggle to get you an accurate solution. And the situations where they struggle is when the geometry that you're trying to mesh doesn't exactly fit or doesn't exactly look like a fully fleshed out three-dimensional object. Okay. Which I guess is a very weird way of saying that. I try to say it in a way to kind of build some suspense, but maybe I should just say it straight up. But so these elements tend to struggle whenever your geometry is either very thin or very slender. Okay. In other words, whenever one of the dimensions of your geometry is much smaller or much bigger than the others. So for instance, the very classical kind of example for two-dimensional object that would very much struggle with solid elements is a very thin plate. The other classical example of a type of geometry that a solid element will struggle with is a slender rod. Okay. Right. So that's what I mean by thin and slender. Okay. Okay. Now it's not that you can't mesh these types of geometries. In fact, we've already seen these types of geometries. Activity 3 comes to mind, right? So in ANSYS activity 3, we meshed a signpost where the post itself was essentially a rod. I wouldn't exactly call it slender, but it is a rod shape, and the sign itself was fairly thin. Okay. So what can happen sometimes is that if your geometry is so thin, right, and you try to put a mesh on this. So a mesh would probably look something like this. But for the rod, maybe just look something like this. Which, when you look at it like that, may not look that bad, or it may not look like anything's wrong. And sometimes sometimes it doesn't cause issues. But, the thing that's a little bit challenging with these types of geometries is that, if you look through the thickness, right? So if you look at our thin plate here, right? Let me kind of zoom in just so you can see, right? So if you look at our thin plate here, we can see that as we go from the top of the plate to the bottom, we only cross over one element here. Okay. So I believe I mentioned this before. And so in these situations, what we say is that there is only one element through the thickness of our geometry. Right. So this is generally a situation that you want to avoid. Right. And so if you're going to be meshing apart, and so I believe we talked about it in activity 2, right? And so if you're going to be producing a mesh with solid elements, you want to make sure that there's at least two and even more elements through the entire thickness of the whatever part that you're looking. So we're going to go into more detail about why it's important to have multiple elements. But just to kind of give you a just an upshot is that we need to have interior nodes. Those interior nodes are very important for the solution. Okay. Okay. So you might look at that and say, okay, that's fine. And so one way we can solve this is we can just refine our mesh, right? That's a solution to most problems in finite elements. Granted that you have enough computing power. So one way to ensure that we have multiple elements through the thickness is that if we know what that thickness is, right? So let's say that thickness is only about 5 millimeters. If we make our elements smaller than that, so we make our elements 2.5 millimeters, then we're guaranteed to have at least one element through the thickness because our elements are naturally smaller than the thickness of the plate. So again, that's something you can do. That's kind of the terminology that we typically use in the field is that this is kind of a brute force solution to your problem. Just throw more computing at it, right? So this works up until a certain point when you kind of run out of computational resources. And so what we say is that, refining the mesh, kind of, just killing it with elements is effective, but it is inefficient, okay? Because probably, once you refine the mesh that small, you probably went way past the point of mesh convergence. And so your solution is already it already has enough elements. It probably had enough, 10 meshes ago. But, you kind of killed it at that point. And so you're kind of wasting a lot of resources. And so it kind of begs the question of, are there better ways for us to deal with these types of geometries that doesn't involve, heavily refining the mesh? And of course, there is. Otherwise, I wouldn't bring it up. Okay, so the better way for us to deal with this is to instead use element types that better match the geometry or the geometrical features of the part that we're trying to mesh. And so what do I mean by that, right? So for a very thin structure, so like let's go back to our thin plate here, right? This reminds us a little bit about our ANSYS activity one, right? So in ANSYS activity one, right, we had our very thin plate with a hole. And so what do we do in that situation? We didn't treat it like a three-dimensional scenario. We treated it as like if it were a two-dimensional scenario, right? And we used two-dimensional elements. And so what if we did the same thing here? And then for the slender geometries, that's essentially a one-dimensional structure, right? So what if we instead use kind of lower dimensional elements to mesh these structures? Right, so 2D or even 1D element. I know we haven't talked about 1D elements just because 1D elements are just very simple. They're just line segments, but they do exist. And in fact, they're called beam elements. Okay. Okay, so that's definitely the approach that we're going to take. And so we're going to use these lower dimensional elements, but we're not going to treat it as if it were a 2D or one-dimensional problem. Okay. And so, we're still going to conduct our analysis in 3D. The only difference is that we're going to use 2D and 1D elements where it's appropriate in our geometry. Okay. The main reason is that if we treat it purely as a 2D or 1D problem, we're not able to obtain any out of plane motion. Oops. right? So we're not going to treat it like activity one. So in activity one, it's a little bit of a subtle kind of difference. Activity one, technically we use shell elements for that, but it wasn't a true shell element because the entirety of activity one took place within that two-dimensional plane. Okay. We want to have situations here where we use two-dimensional elements, but our structure is able to deform into and out of the plane. In other words, if we have kind of a two-dimensional shell like this, right? Right. We want to look at situations where, we apply a force that's perpendicular to the shell, right? Let's say that we apply a force down that way, so essentially like a bending force, right? We want to be able to simulate what it would do in that situation where, we expect the plate to bend or the shell to bend, right? And so it will look something like this. Right? So that's not something you can get from a pure two-dimensional or one-dimensional problem, right? So you go back to activity one, right? If you go back to activity one, it's impossible for you to apply any forces or modes in that z direction because we're treating it as purely 2D. Okay, so here we're doing something different. Here, we're still treating it as a three-dimensional problem. We're just using 2D elements and 1D elements. Okay, so these types of elements here, which are essentially 2D and 1D elements, but do support out-of-plane motion, are called shell and beam elements. All right, so that's the subject of the lecture today, and that's the subject of our activity 4 is going to be, how to utilize these special element types. First of all, how to even get them, how to even, get them into our analysis and kind of how do we utilize them effectively. Okay. And so the basic idea is that, when you have geometrical features that are very difficult for you to mesh with the pure solid elements, you can instead convert those sections of the geometry to shells and beams so that you can mesh it more efficiently, but you don't sacrifice any accuracy. In fact, in a lot of situations, they actually improve your convergence. And so you reach convergence much faster if you use these shell and beam elements in the scenario where they're designed to work. Okay. All right. Any questions on this so far? Okay, good. All right. So what's the difference then, right? So how do these elements actually work? Well, in a pure two-dimensional and one-dimensional problem, we only compute deformations that occur in those dimensions. And so think back to activity 1, right? We had our two-dimensional analysis of a plate with a hole, right? This is taking place in the XY plane, right? When we computed our solution here and we computed the deformation only had two components. It only had a deformation in the X direction and a deformation in the Y direction. right? Because we're treating it as a pure two-dimensional problem. For shell elements and beam elements, we also get the deformations in the z direction as well. Okay. So there's that out-of-plane component that we can actually compute, right? But that's not the only thing that shells and beams compute, right? And so it's not, it's more than just computing the out of plane deformation. It also computes something that the solid elements do not compute at all. Just because for the solid elements, this is kind of just implied by the geometry of the solution, okay? But when you're reducing the dimensionality of an element, you have to compute additional information in order for us to get the full solution in those, in full 3D, okay? And so the other thing that it also computes are what are called rotational degrees of freedom. We have Rx, Ry, and Rz. Right. And so I think, probably more traditional, you've known these as more angular deformations. Okay. So it's actually quite interesting. So for shell and beam elements, we're actually computing more degrees of freedom per node, where, in a pure solid element, you're only computing the deformation. So that's X, Y, and Z. That's only 3 degrees of freedom. But for shells and beams, just because they are lower dimensional elements, we have to compute these additional rotational degrees of freedom in order to have them be compatible with our governing equation. Because the idea is that, even with these specialized elements here, we're still solving the same governing equations for structural mechanics, but, in order for the shape functions for these elements to be compatible with that governing equation, we have to compute these additional degrees of freedom. Okay? Right. So per element, right, you're computing more stuff, but in the end, the idea is that if you use shell and beam elements, overall, you're saving on computational costs because you need way less shell elements or way less beam elements in order to mesh your geometry than if you try to use a solid element. Okay. And so those rotational elements also have another purpose as well. So those rotational degrees of freedom also help with computing solution derivatives inside the element. Okay. In fact, those rotational degrees of freedom, the way that a solid element would compute that is that it would compute the derivatives of the deformation, right? And so in some ways, we're computing those derivative quantities more directly through the use of shell and beam elements. Okay. Okay. So this part here is actually very important, and it's one of the main motivations of why we use these shell and beam elements. Because the reason why it's not recommended or not kind of frowned upon to use solid elements for these is that if you were to try to compute a derivative-based quantity from a thin structure with solid elements, that's usually when things start to break down. Okay. And for us, the main derivative-based quantity that we're mostly worried about are the stress and the strain. Right? So let me kind of illustrate it for you just so you can kind of see, right? So if we have a thin structure here, okay, right? So we're just looking at just the cross section, right? And we have, we just have one layer of elements that are going through the thickness here. And so of course, there's a three-dimensional structure here. So, we have the elements going to go to that here as well. Right, so we have a structure here with just a single layer of elements, right? Right, and so what happens here is that when you only have a single layer of elements, all of the nodes for these elements are sitting on a boundary. So this node, this node, this node, this node, this node, this node, right? You can kind of search all of them. They're all, sitting on the boundary, okay? Now, why is that an issue? And so when you have traditional solid elements, remember, the way that we typically compute derivative-based quantities is through a finite difference approximation, okay? So we're basically taking, the solution at node 1 here, okay? And the solution at node 2, and we're taking the difference between them and we're dividing by the distance, right? And so, for example, du dy. Right, so if the distance between node 1 and node 2 there is dy, right, then the derivative would be the difference in their solution divided by the distance in between. The difference in the solution divided by the distance in between. Okay. Okay. When you have nodes on the boundary like this, remember, all nodes on the boundary have some kind of boundary condition applied to them. Okay. A lot of times, it's just the stress-free boundary condition, but they do have a boundary condition applied on it in some way, shape, or form. Right. And so in some sense, when we take a derivative of two nodes that are on the boundary, we're kind of presetting our derivative from the beginning because, the boundary condition is usually something we have control over. Okay. And so that derivative is not that derivative that we compute based on just those boundary nodes, is not indicative of what the strain or stress actually is. All that's really showing is just what the difference in the two boundary solutions are. And so what we say is that the derivative that we compute from that is kind of too heavily influenced by those boundary conditions. Okay? The other thing is that, oftentimes for these thin structures, you want to find out, or it's a quantity of grave importance for us to see, how things like the strain and the stress, how they develop in such a thin part here, right? And so, probably what might happen, and you can imagine, maybe this part here isn't bending, right? You might have a stress concentration in the middle of this, in between these two parts here. But if you have only one element of the thickness, that's going to be impossible for us to pick up because, we don't pick up any aspect of the interior solution in that derivative. So that's why that, if when you are meshing with solid elements, and this advice is true, no matter if you're doing thin geometries or slender geometries, right? This could even happen, for regular geometries too. So this was an issue in activity 2, right? You want to make sure that there are at least 2 elements with a thickness, right? And so if we were to modify this mesh, right? Right, so let's say that we kind of sandwich another layer of elements in here just like that. So what we obtain from this, and everything that I'm circling in purple here, these are what we call interior nodes. So interior nodes are important because your interior nodes are not going to be directly influenced by the boundary conditions. They are going to be affected by the boundary conditions, so don't get me wrong. The boundary conditions are going to affect their solution, but your interior nodes are more, they're more influenced by the governing equation and what's happening on the inside, which is kind of what you want from this, okay? So you want to have an adequate number of interior nodes if you are using solid elements. Okay? The issue, of course, is that, if you have a particularly thin or slender geometry, in order to produce interior nodes, you have to mesh the geometry very, very, very fine, right? And oftentimes that's not feasible or not practical in those situations. And that's where our shell and beam elements come from. Okay? So our shell and beam elements can mesh these geometries. You can use a lower dimensional element, but our shell and beam elements are computing these additional rotational degrees of freedom in order to compute our derivative quantities much more effective. Okay, so there we kind of eliminate our problem of having these interior nodes. Because technically for a shell and beam element, these are 2D and 1D elements. There are no interior nodes because there is no interior because it's a two-dimensional construct, a two-dimensional shape. But we fix that by, additionally computing those rotational degrees of freedom, so that, they're kind of more directly computed instead of relying on these, finite difference approximations for the derivative. Okay, any questions on this so far? Okay, good. All right, so then that kind of begs the question, right? So, now that we kind of know the benefits and what of using shell and beam elements and what benefits that they bring, the question is, when do we use them, right? And so, I've kind of been just talking kind of vaguely today about, if your geometry is thin, you should use a shell element. If your geometry is slender, you should use a beam element. But how thin is thin and how slender is slender, right? And so there's always a question of, you look at a geometry, is this thin enough or is this slender enough for you to use a beam or a shell? And so to start, we can just say that shell elements are our 2D elements. So shell elements should be used when our geometry is thin enough. Okay. Whereas beam elements are one-dimensional, elements. Those are used when our geometry is slender. Now, as you use these more and more, you start to get an intuition in terms of, when shells and beams can be used. But it's always useful to have at least a starting point. So for when you're first starting out, just some numbers to kind of look at it and kind of see what's thin and some. Question from the chat. So, question is, I'm not sure if I'm understanding how this is different than just creating a smaller mesh. Yeah, no, that's a good question. So, when we're using shell and beam elements, we're actually using two-dimensional elements instead of three-dimensional. Right? And so, for a thin structure like this, right? Right. So if you were to mesh this with three-dimensional elements, right, you would need to refine it enough so that there's at least two elements through the thickness, right? Because if you put just a standard mesh on this, right, so something kind of like this, and so this is what maybe you might start out with. Right. So a mesh like this wouldn't be adequate because there's only, we can see there's only one element through the thickness. There's no interior nodes here, right? And so one thing you can do is you can make your mesh smaller in order to accommodate for this, right? And so in other words, we can basically just refine the mesh enough to add enough elements just like that, right? But remember, the way that we control mesh size is, we're only control mesh size just by a single edge length, okay? And remember also that generally speaking, ANSYS is going to want to maintain a high quality element. And so you can't just have elements that are kind of distorted like this and kind of smushed, okay? And so when you refine your elements, it's actually refining the dimensions in all three dimensions, okay? And so if you're going to say, right, and so in order for this to happen, right, this distance right here, right, the distance that's kind of the half thickness, that's what you would set the edge length to be. Okay? But you're not setting that mesh size only in that direction. It would refine the mesh to that size in every direction. And so what happens then is that you also refine the mesh in the directions that are not thin, right? And so instead of just having a mesh that's thin that way, you also have a mesh that's kind of thin this way as well. And I'm not going to do this throughout the entire structure, but okay. And so yes, you refine the mesh enough in order to get elements through the thickness like that, but then you're also kind of you're being a little bit inefficient because you're adding so many elements in this direction and in this direction, right? Elements that you don't necessarily need because maybe you've already reached convergence in those directions way earlier, but you would need to do that in order to get this interior node here. Okay, so it is something you can do, but it comes at a steeper cost. And so kind of the way that my old colleague would describe it is that, the juice is not worth the squeeze, right? And so you would have to kind of squeeze very hard and work very hard to kind of get that one interior node in there. But you kind of sacrifice the cost in your other directions as well. Okay. So the difference then is that, what we're saying is that instead of trying to mesh this as if it were a three-dimensional object, when you have a thin structure like this, it's essentially 2 dimensions, right? And so what we're going to do instead is we're going to replace this essentially with a 2-dimensional representation. Right? And then on this 2-dimensional representation, we're going to replace this with 2-dimensional elements, right? Which are our shell elements, right? And with the shell elements are special because they compute those extra degrees of freedom where, you don't have to refine it like crazy in order for you to get a converged solution, right? And so your 2-dimensional shell element mesh might look something like this, okay? Maybe closer to kind of what you had originally with only one element. Right? And so you end up with a mesh and you end up with a geometry here that's much more efficiently meshed than the original one, where you had to really refine it really thin in order to get, that coveted interior node. Okay. This is going to make it a bit more, sorry. I think I probably should have drawn the 2D representation from before. I got a little bit too caught up in talking about the interior nodes. Great, cool. Okay. All right, under what situations or when should we apply the shell and beam elements, right? So what is thin? So in other words, what does thin enough mean? So there's no rule on it. And if you ask, 2 different engineers, they'll probably give you 2 different answers in terms of what this means. And so I'm going to give you kind of my own rule of thumb for this. But just know this is not a rule, right? So don't go into your job and say, oh, Dr. Tran told me this, and so this is not this. I'm not claiming this. This is just kind of a good metric for you, a good rule of thumb for you to look at. Okay. So my rule of thumb is that, when one of the dimensions is at least 10 times smaller than the other ones, or maybe one dimension is at least 10 times bigger than the other ones, that's a good way for you to indicate that, maybe we should mesh this with a shell or a beam. All right, so what does that mean? So if we have a geometry like this, right? So let's go ahead and put in some dimensions here. So this would be like maybe the width of the structure, right? Maybe the length is going into the page, and then the thickness of the structure is T. Okay, so I would start to consider shell elements if T was 10 times less than W or F. But again, there's nothing magic about the number 10. And so, it's not that you can't use shells if you're at 9.9 or something like that. In fact, there are probably situations where, maybe your aspect ratio is maybe 7 or 8. And then, you would still consider, I would still consider shells there. But if there's a 10x difference, I'd say that's a pretty good candidate. Okay. One other limitation that you have, that's kind of more set by the software, and you'll kind of understand why this is a limitation too, is that whatever section that you're looking to convert into shells, it has to have a constant thickness. And so you can't have a situation where your thickness is changing at different locations. That one's not a suggestion. That's actually a requirement. Okay. So at least the way that ANSYS is kind of handles this, it can't handle shells with variable thickness. And so if you do have something that's tapering or maybe something that just has a non-uniform thickness, then that's something you can't actually convert to shells. There are ways that you can deal with that. That's kind of very much more advanced much more advanced meshing topics. But for our purposes, you would consider that to be kind of a constraint, right? And so your thickness has to be constant. Okay, and so the same thing is for beams. And for beams, the criteria is kind of the opposite. So for beams, the way I look at it is if one dimension is at least 10 times greater than the other ones, then that's an indication that you have a slender geometry. All right, so a beam, maybe looks something like this. Once again, we have the width, we have the thickness, we have the length. Right, and so in this situation, the length is much greater than the width or the thickness, right? So if the length is greater than or equal to 10 times the thickness, or length is greater than or equal to 10 times the width. Okay. And so in those situations, I would consider the beams. Okay, but again, that's just my own rule of thumb, but you'll get your own intuition from this one. Okay. And so just like shells, though, there is a requirement that you need to follow for beams as well. Okay. So in order to have a beam element, the thing that must be constant throughout the beam is actually the cross-sectional shape. So again, you have a situation where you can't have, tapering beams, and so something with the tapering cross section, something where the cross sectional shape is changing. That cross sectional shape has to be constant along the beam, right? So this beam that I've drawn here, I've drawn a rectangular beam, but you can have an I beam, you can have an L beam, circular beam like a rod. So all those work as long as the cross section stays constant throughout the entire beam, then you can convert that to a beam element. Okay. Because what actually happens is that ANSYS actually stores that cross-sectional information, and it does affect how the solution is actually computed as well. Okay. Okay, so those are the criteria that you can use to know when to apply shells and beams. Okay, any questions on this? Okay, good. Okay, so the next thing we're going to talk about is, how do we even actually make these, right? So how to create shells and beams is kind of more or less software dependent. And so ANSYS kind of has its own way of creating these. That's what I'm going to teach you. But other softwares have other preferred methods. And even within ANSYS, there are multiple different ways to create shells and beams as well. I'm going to focus on just the ones that we're going to use, but I will mention some of the other ones as well. Okay. So the primary method for making shell elements within ANSYS is to do something called a mid-surface operation. So the reason I want to focus on the mid-surface is that, generally this is going to be the operation that you use because, for the most part, the way that people use ANSYS is that you create the CAD file in another software like SolidWorks, you import it into ANSYS, and then you need to modify the geometry from that 3D CAD file. Okay, so mid-surface basically gives us a way to modify an already existing three-dimensional CAD file in order to, fit it for shells. Okay. All the other methods for creating shells kind of involve creating the shell, from the very beginning. And so you kind of have to make your CAD file with the intention that you're going to create shells. And so that does take some foresight and honestly, you get better results that way. But practically speaking, using a bit surface is probably what most people are going to do. And it's perfectly adequate for most situations as well. Okay. Okay, so how does the mid-surface work? So just like the name implies, we're going to create a surface in the middle of two others. Okay. Okay, so here's how it works. And so let me draw it out for you first, and then we'll kind of explain it in text. Okay, okay, so let's say you have a section of a geometry that is, maybe well suited for a shell element. Right? So let's say we have a relatively thin structure, and just to kind of spice things up a little bit, I drew this one vertical instead of horizontal. Okay. Right, so we have a section of our 3D CAD that has a constant thickness, and it's suitable for creating or converting into a shell. Okay. Okay. So essentially what we want to do is that, we're going to identify this section of the geometry, and we're going to create a surface that goes right down the middle of this thickness here. And so we're going to say this is our three-dimensional geometry. We're going to replace this with a two-dimensional sheet, which is going to be our mid-surface. Okay. So that's the idea, right? So we're going to be, just basically eliminating that thickness and creating a two-dimensional kind of representation right down the middle. Okay. The way we do this is that it's kind of actually a two-step process. Okay. So in order to do a mid-surface, you basically have to identify the two surfaces that are parallel to each other. All right. So the way it's going to work is that the first thing we're going to do is we're going to click on one surface of our three-dimensional geometry. Okay. So you're going to click on one side of the thin 3D geometry. Okay. Then you're going to click on the surface that's parallel to that original one. Okay. So I can't highlight it without making a mess, but just imagine we're clicking on the surface that's behind here. Okay. right? So you're going to click on basically the two parallel surfaces. ANSYS is going to do a quick check just to make sure that they are parallel. And if they are parallel, right? And so if they're parallel surfaces, that means the thickness or the distance in between those two planes are constant and uniform, right? And so if it passes those checks, then ANSYS will let you create the mid surface. And so then the three-dimensional geometry will be eliminated, and then it'll be instead replaced with that just 2D slice. Okay. And so in red there, that would be step 3. Okay. So very straightforward, actually. And so, it actually takes longer to explain than it does to actually do, right? But it's really literally just a few clicks. And so you basically set up the mid-surface tool. You click one surface, you click the other one. If you know what you're doing, then they're going to be parallel, and you hit OK, and then the operation is done. So it happens all very quickly, but it kind of helps to kind of know what's going on. Okay, any questions on the mid-surface operation? Okay. One thing to note is that through the mid-surface operation, ANSYS is actually saving an additional piece of information. And so even though geometrically we are eliminating the thickness of this geometry here, that thickness is not forgotten, right? And so that thickness instead is saved as essentially like a material property for this section of or where the shell is. So some people ask me after activity 1, right? So in activity 1, we assign the thickness of that plate, but we don't actually see it, right? I think people were kind of comparing it to like an extrude operation in SolidWorks, right? So we were setting the thickness, but our structure remained 2 dimensions. And so kind of what I told those people at the time was that thickness is being saved. It's just not being represented geometrically. It's just being saved as an additional material property that gets input into the governing equations. Okay, so it's the same thing here. And so, even though we're creating a 2-dimensional surface, we're still solving our equations in 3 dimensions. And so any dimension or any part that we kind of simplify, we still need to save it in some way. Otherwise, our structure is not going to be as stiff as it needs to. Okay, good. All right, so mid-surface, pretty straightforward. Again, it kind of takes longer to explain than to actually do. Let's talk beam elements. Or I guess I'll mention briefly, so this I would say is, the mid-surface is kind of the standard way of creating shells from an already existing 3-dimensional CAD file. The other way, or the other common way to make shells is to kind of construct your CAD file from the beginning and have shells in there, just as parts. So you don't even bother, creating a 3-dimensional CAD. Okay. So that's good, if you kind of know that your end goal is going to be a finite element analysis from the beginning, you can make your CAD file to account for that. But, if you're going to be manufacturing your part or kind of doing anything with it, this kind of just adds an extra step, because then, in order to actually manufacture your part, in order to create the drawings that you need to give to a machinist, you're going to need to CAD it up with the full 3-dimensional geometric thickness anyway. And so that's why it's not as common. But for situations where you're just doing analysis, you're not necessarily going to be manufacturing, and you kind of want to make sure that your shells are created well, then creating it from scratch is an option, right? So I just wanted to mention that, but it's not something we're going to do in this class. Okay, so let's talk about how to find beam elements. Okay. So just like shells, there are multiple different ways to create beam elements. There is kind of the standard way that, very similar to the mid-surface. There's a way to take a three-dimensional CAD file and extract beams from it. Okay, that's going to be the standard way. That's what we're going to use. There's also a manual way as well. So, just like we just finished talking about, if you're creating your CAD file from scratch, then, you can kind of make the beam elements directly in there as just one-dimensional lines. Okay, so both are valid, but again, for the most part, you're going to be using an extraction operation. Okay. So the nice thing is that the extraction tool is actually very easy. There's actually not even much to kind of explain for it. Okay. So the way the extraction tool works is that it's basically a feature that you activate within ANSYS itself. Okay. Then what you do is you just point and click at the portions of your geometry that can be converted to beams, and then that's it. Okay. So it's very easy, right? And so you just kind of just point and click. Another thing that, even though that was a very short explanation, that explanation also will be longer than actually applying. Okay. Right. And so, if you have your geometry, so let's say it looks something like this. You click the extract tool, you just simply just point and click, and then voila. Then your geometry or your beam is converted to a one-dimensional element. Now, one thing that ANSYS is going to check, and so when you do activate the extract feature and you do click on something, ANSYS does check to see that the cross-section is constant. Okay. Okay. Otherwise the extract operation is going to fail. Okay. Okay. And just like the mid-surface operation, when you do the extraction, right? Remember that the cross section of a beam is actually very important for its structural response, right? And so ANSYS actually does actually save that cross sectional shape, okay? And similar to the thickness of a shell, that cross sectional shape is saved as a material property for your special beam methods. Okay. Now, saving a cross section is a bit more complicated. It's not simply like a thickness, where the thickness is simply just a number that it saves, right? So ANSYS actually does save like an image of your cross sectional shape with all the dimensions there, and it probably uses that to compute things like the moment of inertia, which is used to compute the bending and all that good stuff. Okay, but that information is saved, and that's why the cross section has to be constant because it has to be saved as a constant throughout the entire beam. Okay, any questions on beam extraction? The nice thing about the summer session is that, you'll actually, you won't have to wait for long. And so, in the typical semester, this is kind of separated between two different lecture days. And so this would be near the end of lecture one, and then you'd wait 2 days, and then we'd actually apply it in the ANSYS activity. Here, you only have to wait like 10 minutes, and then we're going to apply it. So you'll actually get to see this in action very, very soon. Okay. Okay, so the last point I wanted to cover before we head to break is just some practical issues that occur when you're converting a three-dimensional CAD file to shells and beams. Okay. All right, so I will say I will preface this. I think ANSYS activity 4 is probably my least favorite activity, just because um, it is very annoying. There are a lot of extra steps that we have to do. The actual extraction and the beam, the actual beam extraction and the shell mid surfacing, that part is fun. But what comes after that is actually quite annoying and probably what we're going to spend most of our time. And so I will say that, generally speaking, not everyone gets to finish everything associated with activity 4. So just kind of be prepared to kind of have to finish some stuff at home. I will try to get to the end, just so that you can look back at the video and kind of use as a reference. But just know that these practical issues, they do take a while to kind of address. Okay, and there are a few of them. There's several. Okay. So the first practical issue that can occur is that when you're doing things like you're creating mid surfaces, you're creating extractions, right? We're eliminating geometric thickness in our models, right? Which is good. That's what we want, right? Because we want to be able to mesh these more easily. But this also creates gaps in our model. And so all of a sudden, when you convert certain parts of your geometry to shells and beams, you have these gaps that were not there before. Right? Let me explain. So let's say that you have a geometry like this, right? So let's say we have a thin geometry, that, okay, right? And then this is connected to another thin geometry just like this. First, we have kind of like a T intersection here, right? So in your purely three-dimensional geometry, right? Our two parts here are making contact right at that interface. So think about ANSYS activity 3, right? So we had the connection between the sign and the post, right? We had basically two different parts, but they were in direct contact with each other, which was important for our simulation, okay? Now the issue is that, if you converted this to shells, right? Because we've identified that both of these are, they're both thin, right? So we're going to perform mid-surface operation. And so the left-hand side, right? We've now replaced that with just a simple sheet just like that. Okay? Whereas before, the thickness was, something like this. And same thing for the other part as well, right? And so we've replaced that with just a two-dimensional sheet just like that. Okay, I know I did a very poor job drawing this, but hopefully this is enough to kind of illustrate, right? Because we eliminated the geometric thickness of that first part, right? There's no longer a contact surface between that plate and the other plate, okay? And so in this section here, okay, instead of there being kind of a nice bonded contact, we instead have a gap. Right? And we can't run a finite element simulation if we have a gap, because then those parts are not going to be properly connected. Okay. So after we create the mid surface and before we import the part into actually running the simulation, we have to close every single gap in our geometry. Okay. And so thankfully there are ways to do this, right? And so there are tools within ANSYS to do this just because it is a common problem, but it doesn't work automatically right away. And so, oftentimes we're gonna have to finagle with your geometry a little bit in order to get it to work. Okay. And the geometry that I chose for activity 4 was actually on purpose because what you're going to see is that the geometry for activity 4 is not the best constructed geometry. It's poorly dimensioned and there's kind of a lot of mistakes actually. And so there's a lot for us to clean up. But that's kind of on purpose, just to kind of give you practice in saying that, if you have these kind of imperfections, that there's ways that you could fix it. Okay, so along this lines, and so kind of along the same idea that gaps are being created. Okay. Another thing that can happen is that when you create or when you eliminate these geometric thicknesses or geometric cross sections, then what can also happen is that parts are not going to be aligned like they were before. Okay, so let me give you an example. Okay, so this is going to happen in activity 4. All right, so let's say we have a beam. It's like this. Okay. And let's say that this beam is connecting two halves of our geometry, right? And so we're going to have one half that's like this, another half that's like this. So the beam is not kind of perfectly, centered within the structure. There's a little bit of an offset, but that's just how it was created. Okay. Okay, so what happens when you convert this to a beam, right? So we're going to basically replace this entire three-dimensional beam here with just a single line. What can happen is that this beam is not going to be fully aligned with the structure anymore. Okay? So let's say we create the beam, and generally speaking, the location of where the beam is created is usually created at the centroid of wherever beam that you're extracting. Okay. But now what happened here? Right? And so what happened here is that after we perform this extraction, right, our beam is no longer going to be aligned with our geometry. There's again. And once again, we can't run our geometry like this. We can't run a simulation like this. We have to close the gap. This one is a little bit more complicated though, because we can't simply just close the gap, right? We have to actually move the beam upwards a little bit. Okay? So what we're going to do is we're going to click the beam and actually just kind of nudge it upwards until it's aligned where it should be. Okay. Okay, and so that's one thing that we're going to have to do as well. Okay. All right, and then the last kind of thing that can happen, okay, kind of as a result of one and two, the fact that gaps are created and things get misaligned. What that also does is that it breaks the connections between different parts of your geometry. Okay? And so if you remember from activity three, right, when we saw we took a look at the connections at that point. We didn't do anything with them, but we saw that our sine and our post were connected by a bonded connection, right? Right. So usually ANSYS will create those automatically. And so whenever it detects two parts that are in contact with each other, uh, whenever the part was made, then it'll make those contacts just automatically. But when you're modifying your geometry, you're creating shells and beams, all these connections get broken, right? And so before you can run a simulation, you have to set these connections, you have to reset them manually. So again, another part of the activity that's going to be slightly annoying, but but it has to be done. Otherwise, your simulation's not going to run. Okay. Okay. And so for activity four, the majority of our time is going to be dealing with these three issues that occur. Okay. So again, activity four, not my favorite. It is very tedious. There's kind of a lot of fixing we have to do. But if your geometry is well suited for shells and beams, it really does save you a lot of computational resources. And a lot of times it's necessary. Otherwise, you would need millions and millions of elements to mesh your geometry. Okay, any questions on this before we take a break? Okay, all right, so let's take a break. So let's come back at 4:30 and then we will do our activity. And while we're on break, I'll actually start ANSYS this time, and just so we're not starting from scratch. And so if you're following along from home, go ahead and start ANSYS workbench, and then we will start from. All right, it's 4:30. Let's go ahead and get started. Okay, so hopefully everyone was able to down or start ANSYS Workbench because it does take a bit of time. And then also just like the previous activities, you can go to Canvas and download the instructions for the activity as well as the CAD file. Okay? So the subject for our activity this time is going to be this bridge. Okay? It's not a CAD file of a real bridge. I think this was just a student's, baby's first CAD file on, if I'm going to be completely honest. But it's a great example to use for shells and beams because it has a lot of issues. Some of them kind of unforced errors, right? Some of them don't have to be issues. They're kind of just result of just kind of poor dimensioning on this part. But they're a good illustration of how you need to clean up a model for shells and beams because at the end of the day once we kind of get through all this, you actually end up with a very nice model here that is all shells and beams and is much more efficient than if you tried to mesh it regularly. Okay. Now, I will make an admission right now that I am a little caught on the back foot. So the main program, we were going to use a new program within ANSYS to actually perform the mid surfaces and the extractions and the cleaning up called Space Claim. But I found out at the beginning of break, and I just searched my phone too, that ANSYS has actually discontinued Space Claim as an application within the ANSYS suite. So they've since replaced it with another software called Discovery, which, according to Reddit, is the same. It does all the same thing, but I think the buttons are going to be in a little bit different place. I'm flying a little bit by the seat of my pants here, and so you have to forgive me if I'm kind of fumbling around a little bit. I'm all of these shells and beams are pretty core features within ANSYS, so I don't think I highly doubt that they straight up eliminated them. But I think it might take a little bit of discovering to find out where the new buttons are. Pun intended with discovery. Okay. Okay. So to start, let's go ahead and go make sure you download the instructions. Make sure you download the CAD file. So where I'm starting at is I've already opened up Workbench. I've gone ahead and set a static structural simulation. I've imported my geometry. Okay. So I've right-clicked here and imported just like before. Right, and then what we're going to do, we're going to right click on geometry and then we're going to edit geometry in Discovery. Okay. So hopefully everyone is here and hopefully people aren't just going to be following the PDF because the PDF does have the instructions in Space Plane, but we're going to find out in real time kind of how everything is in Discovery versus Space Plane. Okay. Okay, so let's go ahead and do that and then we will start our adventure. Okay, so the big difference you're going to see here is that when you are working with shells and beams, and when you're converting stuff to shells and beams, you do have to do quite a bit of work in the CAD file before we open up ANSYS Mechanical. So ANSYS Mechanical, we're not going to bring up until actually kind of the very end. Once we're ready to mesh and apply boundary conditions simply. Okay? But the majority of our time is going to be within ANSYS Discovery. I think probably what I'll do is that if so the next week or so is going to be pretty busy for me, just because I want to make sure I grade you guys' midterm projects early next week too. I'll try to find some time to update the activity for PDF, to update the screenshots for Discovery instead of Space Time. Yeah, I'll try to find some time, but no guarantees because I with how short the summer session is, I don't want to leave the midterm projects ungraded for a week. And so I want to make sure I want to try to grade those before our first class session next Tuesday. And then by Tuesday, we're already kind of moving on to the next thing. And of course, Discovery takes a bajillion years to start up. never easy switching to a new software. And I think what they kind of the trend nowadays is to kind of jam pack a lot of these new softwares with a lot of extra features. Um, supposedly this ANSYS Discovery has some AI tools kind of associated with it. I've never used them, obviously. This is gonna be my first time opening up this just the Discovery application. But with all those extra features comes extra loading time as well. Yeah.
Was Space Claim discontinued on the most recent version?
I think so, yeah.
Because I still have that option on mine.
Oh, really? Okay. So if you still have it, you can open in Space Time. I think it's gonna be a little bit faster.
Does it matter which one? Because for like the assignment.
For the assignment, it shouldn't matter because we're just using the features for shells and beams. And so at the end of the day, no matter if you did it in Space Claim, you did it in Discovery, you're going to end up in the same place, or at least that's the hope. But for some reason, mine here doesn't have access to Space Claim. So if you have Space Claim available to you, I would go ahead and do that. My guess is that the oh yeah, I need to remind our IT guy to replace the license, but. My guess is that the buttons are going to be in relatively the same place, and the shells and beams that you get at the end should be exactly the same. There we go. Now we're making progress. Thought we were stuck there. This is one thing I don't really like about newer softwares and kind of newer products nowadays. For some reason, I think a lot of the companies think that more features is better. I had to buy a new fridge recently, and it was actually very, a lot of fridges that I got recommended from my friends and family had things like it had like a screen on the front. It can like automatically determine if your food's going to be expired soon and stuff like that. You can play Skyrim on the fridge for whatever reason. I don't want any of that stuff. I just want a fridge just to be a fridge. I just want my food to be cold. That's kind of what I feel about a lot of technology now. It's like too much, man. Let's get back to basics. Okay, so at least we're somewhere, right? We program didn't crash on us. But where is our bridge? Second?
It takes a second.
Oh, okay. Give it a second. But the good news is that a lot of the tabs here that were in Spacetime are here as well. So here's the repair curve, the repair section, the prepare section. Okay. So that's good. We have kind of the mid-surface button here. We have the extract button. I'm guessing it's somewhere too. Yep, extract is here as well. So yeah, we should be able to do everything that we could in Space Claim here in Discovery. We just need our geometry just to load. Should not have put that. Let's see. Design to okay, good. Yeah, so all the buttons are still here. So thankfully it does look like it's a pretty easy transition between Space Claim and Discovery, because everything that we need is here as well. So we are going to need to move things manually. So just like I mentioned, when you do create shells and beams, things become misaligned, and so you do need to move them. Yeah, so everything is here. Just need our geometry to show up. Has anyone able to open up Discovery and get the bridge to show up? Okay. Okay, good. Okay, good. So I'm glad you guys are there. I apologize. I definitely should have tested this before. I did not think that they would. Usually, ANSYS does a pretty good job kind of maintaining their legacy software. Design Modelware was actually their very first CAD software, and so the fact that they're still supporting that means that I would think that they're trying to support Space Claim too. But yeah, this is it's surprising. Yeah, so I'm kind of waiting on the software. I'm kind of waiting on the geometry to appear again too. let me try this. So let's try it. Let me try closing this. Hopefully I don't regret this. So I'm hoping that
Try clicking on the simulation tab.
simulation. Okay.
That's mine's open to that.
No, unfortunately not. Let's see. Maybe just because it was my first time opening Discovery, and so maybe the geometry did not. Yeah, we could import the geometry. My only worry is that it may not be the change that when you do that, you kind of open it up kind of as a standalone. And it's not attached to the project. But let's try that just so we can kind of continue. And so if you're having trouble opening the geometry, go ahead and go to the file menu within ANSYS Discovery. And then let's go to, and just open up the file this way. And you may have to search for all file formats. Okay, so the bridge file that I had you guys download is an IGES file, which is one of the supported CAD file formats. It may not be the default, and so when you open up files, it may only show you discovery type files, but you need to go to all supported files. Okay, so let's go ahead and open that in. Okay, all right, so here is our bridge finally. Okay. All right, so if you weren't able to, if your bridge was not automatically loading, you may have to do it from file. My only worry is that whatever we change here is not going to be saved into our project, and so we're not going to be able to open mechanical from there. But we'll cross that bridge when we get there. Okay. All right, so first, let's go ahead and start preparing our surface. Okay. So let's look at this geometry first. Okay. So now that we have it open in Discovery, we can actually take a look at it. Okay. Okay. So you can see here we have a bridge. Right? Our bridge has a road. It has kind of these two kind of side things here. And we have a lot of these slender beams. Okay. So every single aspect of this geometry here, I would say, can be converted to either a shell or a beam. Okay, so let's start with the shells first, because that's actually quite simple. Okay, so first thing we're going to do, you're going to go up to the Prepare tab here. Okay, so Prepare is kind of in this part here. Okay, so under Prepare, you're going to go to this button here, which is Mid-Surface. So Mid-Surface, you're going to create a mid-surface from two parallel surfaces. So we're going to click that, right? And then just like we discussed in the class, in order to create a mid-surface, you're going to click on the two surfaces that are perfectly parallel to each other with a constant thickness in between. Okay? So first thing we're going to do is we're going to create a shell from the two sides of the bridge. Okay. Let's do this side first. We're going to click on the inner part. Okay, so you just got to click once, and then you're going to slide around, click on the other part. Okay. Okay, and so if all is looking good, then what you should see is that your two surfaces should highlight. So one should be blue, the other one should be green. Okay. Right, and so that means that ANSYS does recognize these as two parallel surfaces. Right, and then to create the mid-surface, looks like you'll have to click on this green check mark just like that. All right, and so after doing so, you can see here that we've created our mid-surface. And so as long as you don't click, you can actually see the kind of the old surface that was there before, right? And so you can zoom in here and see that, kind of grayed out. We can see the old surface, and in the blue, that's the new mid-surface that we just created, which is a shell of the previous one. Okay. And then you can left click once anywhere in the empty space, and you can eliminate the old solid parts. Okay. All right, so that's our first mid-surface. So again, it's a very quick operation, but you have to make sure that you click on two parallel surfaces in order to get. So the zoom in and out is the same as the mouse wheel from before. Not sure why it may not be working. There may be kind of a way to kind of manually zoom in and out. And so if you go to display here, yeah, so you can zoom in this way as well. Yeah, and so if you click on that, I think you kind of zoom in and zoom out just like that. Yeah, so if your mouse wheel isn't working, go to display, go to zoom, and then after you click zoom, you can left click and then slide up and down, and this will let you zoom in. Okay, good. Okay, so let's go ahead and make mid surfaces for the other parts as well. So we need two other mid surfaces here. So we're going to make one for the other side of the bridge. So let's go ahead and do that very quickly. So let's left click on the outer surface here, and then left click on the inner surface. Doesn't matter which order that you do it in. We're going to make a mid surface between them anyway. Okay. So you can see here once again, I've highlighted both. So one is green, one is blue. Okay. We're going to click on the green check mark. Okay. Once again, we have created a mid surface for that as well. Okay. And then let's do one for the road as well. So this is obviously not a realistic road. And so if you're making a road for a bridge, you're not making a road of asphalt that's that thin, right? So again, this is not a realistic bridge, but this is kind of more of an exercise for shelves and beams. Okay. But this road here is essentially, you can think of it as just a very thin metallic plate. Okay. Okay, so once again, we're going to create a mid surface. So click on mid surface here. Click on the upper side of the road, click on the lower surface of the road. It all looks good just like that, okay? And then once again, we're going to click on the green check mark to create the mid surface. All right, and so now we have our shells, right? So we have a shell for each of the sides of the bridge and then one for the roof, okay? All right, so was everyone able to create the mid surfaces from the different parts, the two sides and the road for the bridge? Okay, good. All right, so next step here, we're not going to fix anything just yet. We're going to create the beams first, okay? Okay, so to create the beams, we're going to use this extract tool, okay? And so the extract tool is once again within the prepare tab. Okay, so make sure you're in that one. And then to the left of the mid surface button is a button for extract, okay? It's kind of nice in Discovery. They make the extract button much larger, and Space Claim was actually pretty small up here. Okay. Okay, so go ahead and click extract. And then you're just going to point and click at every single beam in our surface here, right? And so we have quite a few of them. So we have this top one here first. So go ahead and make sure you mouse over it. Make sure it's highlighted yellow. Go ahead and click. Okay. Right, so you can see after we click that, we've replaced it with just a simple line. And we're going to do the same thing for all of the other beams on the bottom as well. Okay, so just make sure, just point and click. Point and click. Okay. Make sure you don't accidentally click the road, right? So make sure when you've highlighted it, make sure you're mousing over it. Make sure you're clicking on just the beam itself. Okay. If you accidentally click something that you weren't supposed to, you can always Control Z, and that will undo your operation. Okay. Okay, great. All right, and so there we go. And so that's our geometry here is converted to shells and beams. Okay. Okay. Now the fun part of the activity, and by fun I mean not fun. Okay. And so we have to fix this geometry now, because by converting this to shells and beams, we've created a bunch of gaps and a bunch of misalignment that we need to address before we move into ANSYS mechanical. Okay. But was everyone able to get to this part here where they have shells and beams for every part? So you should have no solid surfaces remaining in your geometry here. Okay, good. Okay, so first thing we're going to do is we're going to address some of these gaps. Okay, not all of them, because there are some of these beams are misaligned, but we can at least deal with some too. Okay? Okay, so to deal with this, we're going to use the tool called extend, right? So once again, we're still in the prepare tab. Okay. But we're going to use this tool here for extend. Okay. Okay, so go ahead and click that, and if you mouse over the extend button, you can kind of read a little bit of the tooltip in terms of what it's expected to do. Okay, so the extend feature here is going to extend any surface edges or sketch curves up to and intersecting bottom. Okay, so for basically any gaps that we have here, okay, where if we just simply extend it, we're going to close that gap. Okay, so right here you can see here, right, if you kind of mouse around, there's a gap in between this beam in terms of where it should be connected to this part here, just because of the mid surface that we did. Okay. Okay, so let's go ahead and sorry, the mouse controls are slightly different on the space plane. Okay, so let me go ahead and click on extend. Okay. Right, and so what's going to happen after you click extend? It's going to highlight the regions where you can extend the surface. Okay. Okay, so you can see here that one section that it's identified is this part right here, where the distance is about 10 millimeters. So let's go ahead and click OK. Or not. Oh, I'm sorry, we have to do something else here. So right now, when you click the extend tool, it's only going to extend up to a certain distance. And so if it senses a gap that's greater than 10 millimeters, it's not going to close that gap. So we do need to increase this gap. Okay. So instead of 10 millimeters here, let's set it to be 50. Okay. Okay, so now we're cooking, right? So when we set that gap to be 50 millimeters, you can see here that ANSYS has identified these 8 locations where we can extend our beams and have it connect with another part of the geometry. Okay. All right, so let's go ahead and do that. So once you've changed this to 50 millimeters and you see these 8 red dots appear, go ahead and click on the green check mark. Okay. You may have to click it more than once because it kind of does this in batches. Okay. But as you click on this green check mark, you're going to see those red circles kind of disappear. Okay. Now, there is one section of the geometry here that you won't be able to close. Okay. So there's this kind of little, it kind of almost looks like a toothpick that's kind of been dancing on top of the structure here. Okay. This is just an artifact of the CAD file. Remember, I told you this CAD file is not the cleanest. And so the person that created this CAD file, me, kind of left some details in there because I was a little rusty in my CAD skills. Okay. So you can ignore this little surface here, but just make sure that you connect the beams to the bridge at all the other locations here. Okay. So you should have been able to do this for 8 locations. So 2 on top and then 6 on the bottom. Okay. All right. So was everyone able to extend at least those 8 sections of the bridge? Okay, good. Okay, so let's go ahead and disable that. Okay, so the extend tool worked for some of these beams, okay? But if you kind of hover around here, you can see that some of the beams still aren't connected, right? So if you kind of zoom in here, right? Particularly on the bottom. And so we have some beams here that are fully extended. So this one is fine here, okay? But this one is not, okay? So this one has not been extended enough. And you might be wondering, why did the extend tool not work for this beam right here? So the issue for this one here is that the beam is not actually aligned with the bridge. And so if you actually look, and so I'm going to go ahead and change the view here. Okay. Let me zoom in on some of these beams here. All right, so this is one beam that was not connected. It's a little bit hard to see, but there's actually a beam that's kind of right in that location there. Oh, I apologize. Questions from the chat. Okay, good. Okay. So if you kind of look very closely here, there's a little dot kind of in the middle here. So this was a beam that we could not connect from our extend operation. Okay. And the reason for that, you can see, is that it's not aligned, right? And so, this beam is kind of floating in air right now. So if we were to try to extend this, right? I'm going to try to rotate this as best as possible, right? If we were to try to extend this, it would not be able to hit anything, right? Because it's kind of floating in air. It's kind of below the bridge right now. And so in order for us to actually be able to extend this, we need to actually move this beam up a little bit just so that it can be connected to the bridge. Okay? So this little gap right here, this little misalignment, right? So let me go ahead and highlight it with my mouse here. Right, so that distance right there is preventing us from extending this beam and allowing it to extend. Okay, so we need to kind of close that gap. Okay. Okay, but to do that, we actually need to physically move this beam upwards, okay? Okay. So to do that, there is a tool for this. And so, in discovery and space claim, there are ways for us to modify the geometry. So to do that, you're going to go to design. Okay. So you're going to go to the design tab up at the top, and you're going to see there's another tool here for move. Okay. So the move tool, if you highlight over it, okay. So the move tool lets you basically select an object and then basically let you drag it up and down to the location where you want it to go. Okay. So we're basically going to click on this beam and kind of drag it upwards until it's at least intersecting with the bridge side. Okay? Now to do this, the road is kind of in the way. You don't have to do this, but I like to just kind of hide the road here just because it makes things a little bit hard to to look at. So let's go ahead and find it first. Okay. So let's go ahead and hide this road here. Sorry. It's our mid surfaces. Okay. Okay. So to show the list of the mid surface, so actually this is kind of nice too. So if you want to see the full list of your mid surfaces, you're going to go to the section of the menu here called mid surfaces right here. Okay. You're going to click on this arrow, and it's going to show you all the mid surface that you created. And actually in parentheses here, it actually shows you the thickness, which is actually quite nice. Okay. Okay. So the mid surface for our road is the mid surface that was created with a thickness of 6.35 millimeters. Okay. Okay. So we want to hide this for now. Okay. So just because we don't really want it to get in the way of our moving the beams up. Okay. So to hide it, you're going to click on the eyeball next to mid surface 1, 6.35 millimeters. Okay, so we're just hiding it for now, just so that we can kind of do what we. Okay. All right. So for every beam here that's not connected, we need to move it up. So I'm going to start with this one right here. You're probably going to start with a different one just because of how this activity is. The annoying thing is that every single beam here is offset by a different amount, and so we're going to have to measure each and every single one in order to make sure that we move it correctly. Okay. Okay. And okay, good. We have measured tools. Okay. So this is a beam here that we need to move upwards because you can see that it was not connected here. So let's measure how much we need to go up in the Y direction in order for us to close that gap. Okay. So to do that, we're going to go to the measure tab up here. Okay. Okay, so what the measure tab is going to allow us to do is going to allow us to measure different aspects of our geometry. Okay. And we're going to click on the measurement tool just like there. Okay. And we're going to enable this option for show XYZ vector. So we only want to show the distance in the Y direction. Okay. So in order to find out how much we need to move it upwards, we're going to left click once on the beam that we want to move. Okay. And then while that's selected, you're also going to click on the bottom edge of the bridge. Okay. So we want to find out what the Y distance is between the beam here and the bottom edge. Okay. I'm sorry, you need to hold control and click on both. Yes. Okay. Good. Okay. And so again, in order to show the XYZ, distances, you need to click on this option here. So make sure you have both selected. So hold control on your keyboard and click both of these objects here. So click on the beam and the bottom edge of the bridge. You're going to click on show XYZ vectors. Okay. And you're going to see that the distance in between them in the Y direction is 0.4127 millimeters. Okay. So that's how far we're off. In fact, we can kind of look at it from this direction here. See if this works here. Okay, so it's very hard to see. In fact, I'm gonna try to bring this over here. Oops. Missed it. Okay. me go ahead and click on this beam once again, click on this lower edge. Okay. Right, so you can kind of see here, right, that the distance in the y direction between this beam and the bottom of the bridge is 0.4127 millimeters. And so we need to move it up by that amount. Okay. So let me write that down. And so I have the benefit of Zoom here, but you guys probably have notebooks in front of you. 0.4127 millimeter. Okay, so let's go ahead and move it upwards from there. Okay, so now we're going to go back into the design tab here. We're going to click on the movement tool. Right. This goes out of the way. Okay. Now we're going to move this beam upwards. Okay, so with the move tool enabled here, so you're going to click on move. Okay, you're going to left click on the beam once. Make sure you've selected the entire beam. So don't click just the edge. Make sure you select the entire beam. Okay, and then after you select the entire beam, this axes are going to show up. Okay, we want to click and drag this up in the y direction. So you're going to click and hold this blue arrow. Okay. After you click and hold, you're going to see that as you move it up and down, then this number shows up here. Okay. And so you're going to click and drag it up just a little bit, just to indicate that we want to move it in the positive y direction. Okay. Don't worry about the value yet. We're going to set this manually. And so the value that we're going to put here is we need to move it up by an amount that we can at least extend. Okay. So we're going to move it up by 0.41. I'm going to do 413 millimeters. Okay. We want to make sure we move it up slightly more than the distance that we had before, just to make sure that it's intersecting with the bridge. Okay. So input the value, hit enter. Okay. And what it should do is that it should move that beam into position. And so now what you can do is that once you've done that, you can go back to the prepare tab. Okay. You can click on extend. And then from the extend, you can see now that this beam is properly aligned, we can extend it and use it to hit the other parts of the bridge. So go ahead and click the green check mark, green check mark. Okay. So now that beam is in place. Okay. All right. So I know a couple questions in the chat came up. Question. I click on show because vectors, but it doesn't show them X, Y, Z. So if you're in space claim, the XYZ is actually on the left side here. For discovery, I think, and when you click on measure, right? I need to do this for the next one anyway. So you can click on one here. Make sure you have both things selected. So click on one object here, and then hold control and click on the bottom edge of the bridge. Okay. So it should open up this kind of menu with kind of a black kind of background here. And there should be a button here that says show XYZ vectors. That's how you move that. Okay. Okay, so what you're going to do is that you're basically going to repeat that process for the other three beams here. Okay. And you're going to move them up until they intersect with the bridge, and then you're going to extend them so that they're all making contact. Okay, so once you guys go ahead and do that, I'm going to go ahead and kind of answer questions from the chat, just make sure everyone's caught up. But by the time we kind of reconvene, so let's reconvene in maybe about we'll do 4 minutes. So we'll reconvene at 5:08, and so you should have all the beams connected. Okay. Oh, that's so when you click on show XYZ vectors, it doesn't show this this thing here. Yeah, so you just need to move it up just as long as the beam is within plane of the other ones. Don't move it up too much, otherwise it's going to interfere with our connections later. Yeah. Now, so if you're having problems with it, even without the show XYZ vectors, I think it should also show you this entry here for minimum distance between the axes. This should also work as well, granted that you've selected both the beam and the bottom. Yeah, because this, I think, shows kind of the minimum perpendicular distance between the two. Yeah, so even if the show XYZ vectors thing isn't working, then this entry here, minimum distance between axes should also work as well. Time I am going to move this. And be careful, you when you're selecting the move here, you want to make sure that you're not selecting the bottom of the bridge as well, because that'll move both of it up. So when you're clicking move, make sure you only have selected the beam. Okay. Okay, so you want to move each beam differently, and so don't move them up too much. Oh, you set the raw coordinates for the beams to be that, so that they all align. Oh, I guess you can do that as well. That way they're all kind of aligned with each other. Yeah, so as long as they're kind of all near the bottom edge, then that's fine as well. Yeah. Yeah, that's pretty clever actually, to making sure that they're all set to the same Y coordinate. Okay, it's 5:08, but I'll give you guys just maybe one more minute just to make sure we're all. And if I figured out a way, which I hope works. And so if you're having trouble like me earlier getting the bridge to load automatically in Discovery, what we're going to do is that after we're done modifying the geometry, we'll save this as a CAD file, as a Discovery file outside, and then we'll just load that. We'll load that into a new project into ANSYS. Okay. Right, so actually everyone may want to do this as well, just as a way to make sure you save the geometry, because yeah, this is definitely the most annoying, well, one of the most annoying parts of this or actually, let's see. We may be able to open up mechanical straight from here. Interesting. Okay. Discovery's not so bad. Discovery's kind of cool. Only didn't take 7 years to open up. Yeah, so this top beam, don't worry about it. So remember this is just an artifact from the CAD file. This is not going to affect our results at all. The top beam should already be connected, so that one was already kind of aligned with the bridge. The last part actually is going to be the road. And so once you're done with the beams, and I think we'll do it at 510, we're going to move the road down and make sure it intersects with the bridge, and then we'll move it to ANSYS mechanical front. Okay. All right, so hopefully everyone was able to get the beams all connected. Okay. Right, thankfully, Discovery is actually is pretty similar to Space. I don't know why they didn't just implement all these into SpaceClaim. This is basically just SpaceClaim Plus. Okay. All right. So last thing we're going to do here is we need to connect our road. So let's unhide our road here. So let's go to mid surfaces here, and for the road, click on this eyeball so that we can see it again. Okay. And so if we look at our road here, you can see it's also kind of floating in air. And so we need to make sure that it's connected to everything. Okay. It's floating in air and there's a gap. Okay, so the main thing with the road is that we actually need to move it down. So because we've extracted all these beams, we've kind of eliminated the thickness in that direction. So we need to move the road down in order to make sure it connects to those beams. Okay. Okay, so once again, we are going to use the measurement tool. Okay, so click measure. Okay. And we need to find out kind of what the vertical distance that we need to move the road to. Okay. So click on the road. And then you can click on either any of the beams that we just did, or if you want to keep things consistent, we can measure it up to the bottom of the bridge just like that. Okay. Okay. And then once again, we can look at the distance in the y direction. Okay. So this one should be consistent for everyone. And so if you're not able to show the x, y, z vectors, the amount in the y direction you need to move is about 28.373. Okay. Now this one you want to be careful. So for the beams, we moved it up slightly more than the measurement had because we wanted to make sure that we were intersecting. Okay. In this situation, if we move it a little bit too much, we're going to move the road past the bridge because we're coming from the opposite direction. Okay. So the amount that we're actually going to move down is slightly less than this. So let's move it down 28.373. Okay. Okay. So once again, we're going to click on design, click on move. Okay. You want to make sure you click on the entirety of the road. Okay. Don't just click on one edge. Just zoom in. Okay, click on the entirety of the road. Once again, you're going to grab the blue arrow. You're going to move it downwards. Okay. And we're going to set this to 28.373. Okay. Okay, so that should move the road right on top of the beams. Last thing we need to do is we need to close that gap in between the road and the sides of the bridge. So once again, we're going to go to prepare. Okay. Click on extend. Okay. So the nice thing is that the extend tool actually works for shells as well. Okay. So you can see here that it wants to extend both of these edges here. Okay. All right. So go ahead and click on the green check mark. Click OK. All right. And so you can see now that our road is fully connected to the sides of the bridge. Okay. Okay, and so if you did everything like this, then what you should have is you should have your geometry fully converted to shells and beams, and should all the gaps and all of the alignment issues should be fixed. Okay. All right, everyone able to get to this part? Yes.
Could you show that last part, how you connected the bottom part, the road?
Yeah. So we're gonna use the same extend tool. Right, so the same extend tool that we use for the beam. So you're going to go to prepare, click on extend. And so when you click extend, it should highlight the two sides of the road in red. And then you're just going to click on the green check mark in order to extend it. If it's not highlighting in red, you might have moved it down a little bit too far. So I would go ahead and measure it again and then move it up until it's intersecting with the bottom. Okay. Okay, good. And so now that we are done here, let's go ahead and save it just so that we don't lose our work because I'll pass 40 minutes. Okay. Okay, so let's go ahead and save as. And so this is not part of the PDF, right? So this is just a fail save just in case things get messed up. Okay, so we're going to save this as a discovery file, right? And so the name that I'm going to give this is bridges shell B. Okay. And I'm going to save it under downloads, and we're going to save it as a discovery file. Okay. So this is just a fail safe, right? And so this is just in case things mess up and we don't have to go through this entire process again. So let's go ahead and click save. Let's make sure that the file is saved correctly. Okay, good. All right. So you should have a new CAD file here called bridges shell beam, just to kind of save our work. Okay. But if things worked out, if this button does what I think it's going to do, this is going to open up ANSYS Mechanical with this geometry here. Okay. So if you're in Discovery, you can go ahead and click on Mechanical. So that should open up ANSYS Mechanical. If you're working in Space Claim, what you should be able to do, you should be able to close this program for Discovery, go back to Workbench, and then double click on Model to open up Mechanical. Okay. Okay, well, let's go ahead and let's try this button from Discovery here. Let's open a mechanical. Let's see what it does. Part of me is a little bit worried just because the ANSYS is not a lightweight program, and so running both Discovery and ANSYS mechanical together might just kill your entire RAM, but we'll see what happens. Oh man, it opened up another whole workbench. Yeah, either one is okay. Yeah, so the beam in the bottom of the bridge should be at the same location. So the road can be on top of either one of those. Yeah. Okay, so it looks like if you click on the mechanical button within Discovery, it actually opens up another instance of Workbench. So your RAM really might be crying, but here it is. And so we have our surface here, which is great. Okay. So what I'm going to do now that we're in Workbench here, I'm going to go ahead and close my other instance of Workbench. We don't need to save it. It's fine. Okay, Discovery is still open. Let's see if we can close Discovery. Okay, good. So Discovery can close as well. So just to kind of save yourself some RAM, try to make it so that the only programs open should be just the Workbench that is associated with your mechanical and ANSYS mechanical itself. Okay, so if everything goes well and everything is appropriately attached, you should be in ANSYS mechanical with your structure here that's made of shells and beams. All right, everyone able to kind of get to this point here? Okay. Yeah, I'll give it a second. Yeah, it's opening these programs can be pretty heavy, especially for laptop computers as well. Yeah, but we're almost there, I promise. And so all that's left, and so thankfully the meshing and the boundary conditions for this case are pretty straightforward. I'm not going to have you do anything kind of crazy for that. The last thing we need to do is we need to set the connections between the different parts. Yeah, so once you make the road, you can go ahead and transfer the geometry into mechanical. And so if you're in Discovery, there is a button on the top here that says transfer to mechanical. Go ahead and click that. Okay. Other questions? My save button is grayed out, but nothing is running. From Discovery, you can't save your parts. Hopefully it's okay. So go ahead and try opening up ANSYS mechanical. So from Discovery, even if you can't save the part, go ahead and go to the top right corner and click on transfer to mechanical. Okay. See if that works. Okay. Yeah, I wonder if it's another issue with Windows security, like it's blocking certain features of Discovery. I've been reading a bit on people having issues with that as well. Okay, yeah, but the last thing we need to do is we need to form our connections, mesh, boundary conditions, and we're actually making pretty good time. We have 30 more minutes, and so and this is definitely the most annoying activity for sure. And not having access to space claim was kind of a wrench in funds. Okay, all right, so let's go. I'm gonna go ahead and continue. So, but if you're still opening up mechanical, definitely just kind of maybe just kind of listen for now. Okay. Okay. So we have our geometry here. First thing we're going to do is that we're going to click on this part of the geometry here. So it should be like sys 92. Okay. It's the part of our geometry that has a question mark next to it. Okay. So this part, it's a little bit hard to see, but this was kind of this extra kind of little chopstick or little toothpick that was kind of standing on top, just as a fragment of before we kind of constructed CAD. We don't need this for our geometry here, so we're going to go ahead and suppress this. Okay. So just like we did in activity 2, any part that we don't need for our analysis, we can just suppress it. Okay, so we're going to right click on this little geometry here, and then click on suppress bottom. Okay. Good. Okay, so now it's gone. And so now all we're left with is just our parts here. Okay. Okay. So this is probably the most parts that we've seen together in one ANSYS analysis. So every single surface, every single shell, and every single beam has been saved as a separate part. Okay. But right now, none of these parts are actually connected. And so even though geometrically they are next to each other, it's almost as if they're next to each other, but not exactly touching. So we need to tell ANSYS to basically form a bonded connection in between these parts here. Okay. So to make a connection, we're going to right click on connections here. Highlight it with the pen. Okay, so we're going to right click on connections. Okay. We're going to go insert. And then you're going to insert a manual contact region. And so we're basically going to manually set that two parts of our geometry should be in contact, and in particular that they should be bonded to each other. Okay. Okay, so we need to make several of these because we have several parts to connect. The good news is that we can kind of group certain parts together that are going to be similar. Okay. Okay. First thing let's connect the road to all of the beams on the bottom. Okay. Okay. So the way this works is that when you create a manual contact region, in the bottom left-hand side of the screen, you need to select two portions of your geometry. So one is going to be called the contact, and the other one's going to be called the target. Okay. So basically, these are going to be the two sections that are going to be connected, essentially. Okay. Okay. So for the target, okay, let's select the entire road here. Okay, so we're going to left click the entire road, so it's all highlighted. And the good news is that, we've turned this into a shell, so the top and bottom are the same because it's a two-dimensional surface. Okay. Go to target here and then hit apply. Okay. All right, and then for the contact, we're going to select all of the beams on the bottom just to ensure that our road is connected to all of these beams here. Okay. Now, it's going to be a little bit of a delicate process because you have to mouse over the beams exactly. Okay, so zoom in and kind of pan if you have to. Okay. You're going to left click on each of the beams here, holding control on your keyboard to make sure that you're selecting all of them. Select that one. Maybe going from the bottom might be a little bit easier. Okay. All right, so hopefully you've selected all of these beams here on the bottom, okay? And then for the contact, you're going to click on contact and hit apply. Right, and so you should have 7 edges for the contact and 1 face for the road for the target. Okay. All right, and so now we can go ahead and set this contact type. And so we're going to set the contact type to bonded. Okay. That's going to make sure that the road and the beams are fully connected to each other. And that forms that connection there. Okay. All right. So is everyone able to, or everyone that, at least everyone that's at this point here, everyone able to kind of make this connection between the beams and the road? Okay, good. Okay, so now we also need to connect the sides of the beams to the side of the bridge, okay? Because those beams are mechanically connected to the bridge itself. Okay. Okay, so let's go ahead and make another contact region. So we're going to right click on contact, insert, manual contact region. Okay, so we're going to make another one. And once again, we're going to click on one surface here. So let's click on this side of the bridge. Okay. I say this side, but it doesn't have to specifically be this side. It can be whatever side is most convenient for you right now. Okay. Go to the target and hit apply. Okay. That's going to set one side of the bridge to what we want to connect. And then we want to connect the beams to that bridge, but we only want to connect just the ends of the beams here, right? So there's one point right at the end of the beams. And if it's very hard to click unless you zoom in, okay? One thing that can help is that you can change the selection mode up here. And so what you can do is you can change the selection mode here to vertex mode. Okay. That way your mouse is only going to snap to any points in the structure here. Okay. So you're going to click on all the beam ends. And so that includes the one at the top. So you're going to click the one at the top, and then you're going to click on all of the beam ends here on the bottom as well. Okay. Again, holding control on your keyboard to make sure that you select all. And I see there's a question in the chat. I'm just going to finish clicking all of these first, and then I will get to that. Okay. And so for the contact here, you should have 8 vertices, right? So all 8 ends, all 8 points of the beams should be connected to the corresponding side of the bridge. Okay, good. Okay, good. So that's the next contact region there. Okay. We're going to do the same thing on the opposite side. So we're going to make another manual contact region. So you're going to right click on contacts, go to insert, manual contact region. Okay. We're going to select the other side of the beam. You may need to switch back to face selecting mode for this. Okay. So click on that side of the beam, make sure it's highlighted green, set that as the target. Okay. And then we're going to select all the vertices on that side as well. Okay. Okay, so now all sides of the beam are connected to the bridge on that side. Okay. Okay, so now the beams are connected to the bridge. The road is connected to the beams. The last thing that we have to do here is make sure the road is connected to the bridge itself. Okay. Okay, so once again, we're going to right click on contacts, insert manual contact region. Okay. And then we're gonna click on, once again, we're gonna click on one of the sides of the bridge here. Okay. Set that as the target. And what we're gonna connect to that is just the side of the road here. Okay. Now you have to be careful here because we only want to connect just the outer edge of the road itself. Okay. So make sure you're on edge selecting mode. Okay. Click on just the edge of the road here. Okay. Then go ahead and go to contact and hit apply. Okay. All right, and so one thing you should be noticing, and so we saw this in activity 3 as well, as you're creating your contact regions, then the menu here on the right should be highlighting the 2 bodies that are being connected to each other. Okay. Okay, and so we're going to do one more contact. So in total, you should have 5 contact regions. Okay. Take one for the last section here. So let's go ahead and do this. That surface there. Go to edge selector, click on the edge of the road. Apply. Okay. All right, and so these are the 5 contact regions you should have. So you should have 2 contact regions that connect the 2 sides of the roads to the bridge. Okay, so that's what we have here and here. You should have contact regions that connect the ends of the beams to the bridge. Okay, so you have this one here and this one here. Okay, and then finally, you should have a contact region that connects the road to all of the lower beams. Okay, so that's this one, right? So 5 in total. All right, any questions on that? Okay, good. Okay, so from here it's pretty straightforward. So there's not much else to do. Let's just put a default mesh for now. We've kind of done enough here. So I'm just going to right click on generate mesh. Okay. Normally the mesh is normally we want to apply meshing settings on this to modify the size, but this is going to be fine for our purposes just for now. Okay. Notice how the mesh here is we have shells and beams. So we have 2-dimensional mesh elements for our shell parts and 1-dimensional mesh elements for the beam parts. Okay, that's exactly what we want. Okay. Let's go ahead and don't know why it's not showing our solution here. I think probably what happened is because we didn't connect this. We didn't connect this session here to we went straight from discovery. I think that's probably what happened. So because we went straight from discovery, then we don't have the simulation tools available here. So I apologize for that. So I will kind of fix this, but it will take me a bit to kind of go back and fix it. But for now, just because we still have some time, but just so that I'm not wasting your guys' time. The last thing I wanted you guys to do here was apply just some very basic boundary conditions. Okay. So the boundary conditions were for the two edges of the road here. Okay. So from the front end and the back end, you want to apply a fixed support. Okay. Okay. All right, so make sure the two ends of the road are fixed. And then on the top of the road, you're going to apply a downward force. Okay, so the downward force, you can just distribute it equally across the entire road. And so that's meant to represent some cars that are going to be on the road. In this case, they're very tiny cars. This is not a real bridge. This is kind of a Hot Wheels bridge here. But we can put a downward force. Okay. And so once you do that, you can run your simulation, and just like normal, you can display things like the total deformation and the equivalent stress. Okay. And so once you kind of display those, then you can kind of see your results from there. And you should see that the results actually look pretty good. So even though we have two-dimensional elements and one-dimensional elements, you should be able to see that our elements there are kind of deforming out of plane, which is exactly what shell and beam elements are supposed to do. Okay. In fact, if you look at the project specifications here, okay, clear my doodles here. Okay. And so your results should look something like this. And so, this, I believe here is your total deformation. Okay. So you can see that our deformation is maximum in the regions in between the beams, which makes sense because the beams are going to be there to provide strength. And so our deformation should be greatest in the parts which are kind of furthest away from the beams. Okay. And then our stress should look something like this. And so we do have stress concentrations, but they occur at the ends of the road. Okay. Okay. So let's go over the rest of the activity. I'm going to go ahead and fix this here just so you can kind of see, especially for those of you that are kind of watching on the recording. But for those of you that are here, you can go ahead and get started on the rest of the activity. So problem 5 here, I want you to do a mesh convergence test. Okay. So we've already discussed what a mesh convergence test is, but in other times that I've taught this class, I haven't covered that just yet. So the reason this problem is so long is because I'm just explaining what a mesh convergence test is. Okay. So I want you guys to do that for this activity here. Okay. Problem 6, I want you to look at a different support condition. And so, instead of applying a fixed support on both ends, maybe you can apply, fixed supports on all of these here to kind of simulate maybe that these are attached to pillars. Okay. Problem 7, I want you to do a solid element analysis. And so basically, I want you to redo this analysis, but I want you to do it on the original geometry. And so before we convert it to shells and beams. Okay. And so I want you to try doing the analysis on that. I will warn you that problem 7 may not be possible. And so depending on how powerful your computer is, and also kind of depending on how lucky you are, you may be able to run this, but I've seen in the past that I would say maybe 75% of the class just gets an error when trying to mesh and when trying to solve this. And that's kind of the point, right? And so the point is that this geometry here was not really designed to run with solid elements because it has so many thin and slender parts of the geometry, right? And so if you do try to run this analysis with solid elements, then you're going to run into issues, okay? And so if you're not able to get an analysis done, you just get an error. Just report that here. Just say that, we try to run it, and this is the error that I get. That's perfectly fine, okay? Then problem 8 is the quick sum, okay? So this is your one-page report on the results, okay? And since this activity here is quite involved, there's a lot to do. I know probably a lot of people have to go in and redo a lot of the shells and beams. There's no additional exercise. So this activity is just the bridge. Okay. All right. Any questions on the activity? Okay. Okay, all right, so I'm gonna go ahead and see if I can fix this, but that's all that we have time for today. And so, if you're watching on the recording, that should be everything that you need to run the activity. Okay. If you want to see me kind of fix this, go ahead and stick around. Because I think what I need to do is I need to create kind of a new ANSYS mechanical static structural analysis and kind of import that into there. Okay. Should be pretty quick, but I didn't want to make promises before I started. But yeah, if you guys are heading out, thank you guys for coming today. I apologize for the technical difficulties. I didn't know that spacetime was going to be deprecated up until this point, but thankfully discovery was pretty straightforward. Right, so thank you guys for coming. Hope you guys have a good rest of your evening, and I will see you guys tomorrow. Okay, so let's see if we can try to fix this. Okay, so if we close this, then we should come back to ANSYS mechanical here, or ANSYS workbench. Okay, so what I'm really worried about here is I'm hoping all the connections that we just made were saved. Okay. Okay, yeah, so that makes sense. And so when we clicked from discovery to open it up in mechanical, then it didn't do so in a static structural context. It just did so in a blank. Okay, but we can fix this. And so, if you have it like this, what you can do, so ANSYS actually makes it very easy to kind of transfer data in between different modules within the software. And so what we're going to do is we're going to left click on static structural and we're going to drag it. We're going to drag it onto model right here. So what that's going to do is that it's going to create a new instance of static structural, but it's going to link it to the geometry that we just created. Okay. Okay, good. Okay, so now we've created another static structural and it's linked our material properties, it's linked our model, and it should have linked our mesh too. So that's typically what this arrow here as well. Okay. So I'm going to go ahead and double click on setup to open up ANSYS mechanical, and this should kind of fix the issue and allow us to apply boundary conditions to our system. Okay, good, perfect, good. Okay, so doing that, you can see that we've imported our mesh, but now we can apply boundary conditions. So now we have this static structural A file. Okay, so if you're having this issue from before, so you directly open the part from discovery, you click on the button here for open up and transfer to mechanical. What the issue was is that it opened it up in mechanical, but it didn't do so in a static structural context. And so you need to go back to Workbench and then open up static structural, but you need to link it to the mechanical model that we just made. So to do that, you're going to left click on static structural and click and drag it right on top of the model that we just made there. Okay, so from here, we can go ahead and add our boundary condition. So let's go ahead and insert our fixed support. Okay, and we're going to apply this on an edge, or apply this edge here, apply, good. And then let's go ahead and apply a force. Oh. Let's go ahead and apply a force onto our surface here. Okay. Let's go ahead and define this by components. And let's just apply a minus 100 pound force. Okay, so just to kind of see. Okay. And just like before, let's go ahead and specify the total deformation, the stress. Okay, and then let's go ahead and click on solve. Checking to make sure all our contact regions came in. Okay, good. Okay, so a little bit rough here, just because our mesh is quite coarse, but you can see here that this is doing what we expect it to do. Okay, so the road is deforming, and the beam is deforming along with it as well. Okay, so you can see here, even though we applied the force directly onto the road, the beams, that force is being transmitted to the beams because they are connected, and they're being transmitted to the sides of the bridge as well. Okay, so we can clean this up, obviously, so we can go ahead and improve this mesh. So let's make the mesh size, let's make it 1.5 inches. Okay. Let's go ahead and hit solve, and let's see what the results look like. And also, I saw your question, but I'm gonna just make sure that this is running first, and I'll apologize. Okay, so that's a lot more clean right there. Okay, good. Okay, so that's so for those of you hopefully that are maybe watching on this on the recording, you're having issues with discovery, not being able to apply boundary conditions. That's what you need to do. So the fix is to basically go back to Workbench, click and drag static structural onto your mechanical model, and you should be good to go. Okay.
I've got an interesting problem. What's up? Every time I try to do the extract, it turns them sideways.
I've seen that happen sometimes in the past. It thinks for some reason the beam is going in that direction.
Yeah.
Um,
And because of it, it won't let me do the extract on that. So wasn't sure if you are like, oh, that's an easy fix, but
I remember, yeah, someone had this 2 years ago. I forgot exactly what the fix was. Let's sit down and let's look at it.
there's also a possibility I just need to restart my computer. For some reason, the ANSYS I have is temperamental like that.
Okay.
And I restarted the first problem. I restarted like 5 times because
Oh, I
one
see.
mesh shut for me. So
I see. I remember someone had this issue actually on one of the lab computers, and so it's not a unique. But yeah, it's interesting just because I mean technically there is a beam in that direction if you consider the entire thing to be a cross section, but that's obviously not what we want. Can I see that mouse for a second? So let's undo first. So are you able to make the midsections okay?
yeah, I can do midsections. I can do everything except that one beam.
Okay.
And I Googled it, and Google's like, oh, you can just use move. Well,
So you can't do that one, and then when you put these ones, it goes like that. Well, there's like settings for this somewhere. It's not even the right.
Yeah.
That makes no sense at all. Because it should detect the longest, so the way it should work is that it should detect the longest dimension and it should create the beam in that direction. So it should be able to see that the longest dimensions in this X direction here. I guess this might be Z. And it's should create the beam. It shouldn't go in the Y direction. But for some reason, I think when it's trying to force a beam in the Y direction. Yeah, I can't do it in this direction because it's I think what it's trying to find a profile in this direction, but it's not constantly going to circular beam. But it's trying to force it in that ball. Let me get my pen. Let me see if I can sort this.
Strange.
I'll have to look it up a bit more.
Okay.
Let me do a bit of research. But yeah, that is, I remember supposedly someone had this a couple years ago. I don't remember how we fixed it at the end of the day. But yeah, maybe, I mean, you can try restarting your computer, see if that works.
Yeah.
I'd be pleasantly surprised if it worked. But yeah, just let me know if that works or not. But
Okay.
I'll do it more tomorrow.
Sounds good.
Yeah.
Thank you.
Yep.